Right, so when using a use substitution, which is what the change of variable term is known as, so it is also known as, this is what most people call it, U substitution. So when using a U substitution for a definite integral, sometimes it is convenient to rewrite the limits of integration rather than revert back to the original terms of the variable. So when using definite integrals, it is often more convenient or useful to determine the limits of integration for the variable u rather than to convert back to x. So, and then, when you convert back to x, you will have to use the original limits of integration. Especially when your function is very complicated, but its substitution is very easy to manipulate. This change of limits becomes much more convenient. So the following theorem is the change of variables for definite integrals. For definite integrals. And it says the following: if the function u equals g of x has a continuous derivative on the closed interval ab, and f is continuous on the range of f, on the range of g, then the following holds: the antiderivative from a to b of f of g of x, g prime of x dx, is equal to the integral of g of a from g of a to g of b of f of u du. So notice here that instead of using the original limits of integration, we are now evaluating them at the inner function. So we're changing the limits of integration. We're changing the limits of integration. So we are allowed to do this and then evaluate our function at u instead of at g. So for example, let's evaluate the following: the integral from 0 to 1 of x times x squared plus 1 cubed dx. Now to start, let's let u be equal to the inner function x squared plus 1. And that means that u, or du, the derivative, is equal to 2x dx. The derivative of x squared is 2x, and the derivative of 1 is 0. Now, when we talk about our function g is what we're calling u now. When we calculate the new upper and lower limits of integration, and lower limits of integration, we substitute the given limits into our u substitution. So for example, to get the lower limit, let's say the upper limit here, I'm going to be using u. So u is equal to x squared plus 1. What was the lower limit here? The lower limit was 0. The upper limit was 1. So what am I going to do? I'm going to do u is equal to 0 squared plus 1. And here I'm going to do u is equal to 1 squared plus 1. I'm just plugging in the limits. The lower limit was 0, so I'm plugging 0. The upper limit was 1, so I'm plugging in 1. So I get that the upper limit, let's call this u of a and u of b. So the upper limit, the lower limit is going to be 1, and the upper limit is going to be 2. So now we substitute, and we get the following. We had the integral from 0 to 1 of x squared plus 1 cubed dx. That's what we had originally. We had the u substitution, and we let u be x squared plus 1. So now what we have here is x squared plus 1 is going to be u. There's one more thing that I need. I need to find x dx, which I haven't done. I have 2x dx. I need 1x dx. So you divide both sides by 2, and you get x dx is equal to 1/2 du. So what I have here is u, the 1/2 goes on the outside, du, by my substitution, and by the constant multiple rule. And then my new limits of integration are, the lower one is 1, the upper one is 2. So this goes down from 1 to 2. Instead of going from 0 to 1, we are going from 1 to 2. Now, the antiderivative of u is going to be u squared over 2 by the power rule. So it's going to be 1/2 times u squared over 2 evaluated from 1 to 2. Now, because of the fact that we rewrote the limits of integration for u, we do not have to substitute back the x's here. We don't have to put in x squared plus 1 in there. And I actually made a mistake, because this is not just u, this is u cubed. So it should be u cubed. So this should be u to the 4 over 4. There we go. That looks better. Okay, so now we could apply the fundamental theorem of calculus. So I could substitute here, instead of substituting for the x, I could just simply put in the u in there. So I could do 2 to the 4 over 4 minus 1 to the 4 over 4 by the fundamental theorem of calculus. Notice that this is much easier than doing 2 squared plus 1 and then to the 4, and 1 squared plus 1 and then to the 4. So this is equal to 1 over 2 times 2 to the 4. I believe that that's 16 over 4 minus 1/4. So this is going to be equal to 1/2 times 15 over 4, which is equal to 15 over 8. So we have that our solution is 15 over 8. Notice that I did not have to substitute back for x. In fact, if you were to substitute back for x, you'd get the exact same solution. But notice that I rewrote the limits of integration, and our solution was a number, and this number is the answer for the integral in terms of x. Yet I didn't solve that integral, I solved the integral in terms of u. But the answers are actually the same result. You get the same result. If you don't believe me, well, at the point in which we had the 1/2 times u to the 4 over 4 to the 1 to 2, we could have from here, so this is a new problem, so we could have done the following. If you substitute back, this would have been x squared plus 1 to the power 4 divided by 4, and because we substituted back, we have to substitute back our original limits of integration from 0 to 1, not from 1 to 2. And now if you use fundamental theorem, you have 1 squared plus 1 over 4 minus 0 squared plus 1 over 4. So this is equal to 1/2. Did I make a mistake here? To the 4. To the 4. There we go. This is equal to 2 to the 4 over 4 minus 1 to the 4 over 4, which is equal to 1/2 times, again, 16 over 4 minus 1 over 4, and this is going to be the exact same result of 15 over 8. Okay, because that's the exact same thing that we had down here. So the answers are exactly the same, but notice that if you simply substitute it for u here, the work is much simpler because we don't have to square again and add and then take it to the power 4. So this becomes much easier, much simpler. All right, let's do another one. So that was example number 1. Yeah, number 1. Let's do another one. All right, so let's say we wanted to evaluate the following integral, and it's given by a is equal to the integral from 1 to 5 of x over square root of 2x minus 1 dx. Okay, so here we let u be 2x minus 1, which is the inner function here. That means that du is going to be equal to 2 dx. Notice that up here I have an x. I don't have a 2. I have an x. So what I'm going to do is first I'm going to divide by 2 on both sides here. So I'm going to have du over 2 is equal to dx. So now I have a substitution for dx and I have a substitution for 2x minus 1, but I don't have a substitution for x. So let's get the substitution for x from this equation. So I have u is equal to 2x minus 1. So I have u plus 1 is equal to 2x. So we divide by 2 on both sides. So we have u plus 1 over 2 is equal to x. So now I have a substitution for this x up here as well. Because I'm using a substitution, and by the change of variable rule, if I want to use if I want to simply just use u instead of this mammoth of a thing, I have to rewrite the limits of integration. So let's do that. I could use this equation up here to rewrite the limits of integration. So the lower limit, I'm going to write here, and the upper limit here. And remember, u is equal to 2x minus 1. So my lower limit is 1, the upper limit is 5. So what do we have? We have 2 times 1 minus 1, which is equal to 1. Yeah, this is fine. And 2 times 5 minus 1, which is 10 minus 1, which is 9. Okay, hopefully we don't mess this up. Alright, so let's see what we get. So we have the integral, and now it's from 1 to 9 of the following. So we have a value for the x, we have a value for x, and we have a value for radical, for 1 over radical x. And I will have a problem because notice that I'm going to have 1 over radical u. No, this shouldn't be a problem. Let's see what happens. Hopefully this is not a problem. So let's see what happens. So I have a value for x, which I have u plus 1 over 2. So u plus 1 over 2 divided by the square root of u times du and the 1/2 on the outside. This is everything that I had. I had 1/2 du is equal to dx, and I have u plus 1 over 2 is equal to x, and then 2x minus 1 is equal to u. So we could simplify this a little bit. This is equal to u plus 1 over 2 times radical u du. And this is where it's going to get a bit tricky. So let's see what we can do here. Okay, so first of all, let me take out that 1/2 that's on the inside. This 2, I want to take it out. So it's going to make it 1/4. There's the integral from 1 over 9 of u plus 1 divided by radical u du. Okay, then I'm going to rewrite this as 1 over 4 times the integral from 1 over 9 of u divided by u to the 1/2 du plus the integral from 1 to 9 of 1 over radical u du. So this should work. So this is 1 over 4th. This integral right here, first of all, you could rewrite this. Let me rewrite it first. This is going to be u to the 1/2 because 1 minus 1/2 is 1/2 du plus the integral from 1 to 9, and this is u to the minus 1/2 here du. This is equal to 1/4. This antiderivative now is going to be u to the 3/2, so 2 over 3 from 1 to 9. Yep. Plus this integral is going to be, when you add 1 here, it's going to be 1/2 divided by 1/2, so it's going to be 2u to the 1/2 from 1 to 9. So just make sure that's right. So 1 minus 1/2 is 1/2. So 1/2, yeah. So that's correct. Okay, so now we can plug in for our limits of integration. So notice that they both have the same limits of integration, so I could actually write it like this: 1 over 4 times 2u to the 3 over 2 over 3 plus 2u to the 1/2 from 1 to 9. And this is equal to 1/4 times 2 to the 9 to the 3 over 2 over 3 plus 2 to the 9 to the 1/2 minus, so this is my f of b, minus 2 to the 1 to the 3/2 over 3 plus 2 times 1 to the 1/2. Yeah. And this is my f of a. Don't forget the parentheses because you have a negative sign from the fundamental theorem of calculus. So it's important that you put those parentheses in there. So it's equal to 1 over 4. And now the square root of 9 is 3, and 3 cubed is 27. So it's going to be 2 times 27 over 3. I'm not going to do that yet. And then it's going to be plus 2 times 3, which is 6. So the square root of 9 is 3. Minus 2 times 1 over 3. So that's just 2 over 3. Plus 2. This is why I didn't want to combine this yet. So this is 1/4 times, it's going to be, remember how we did that other problem, this is going to be 2 times 27. So let's actually multiply this. So 2 times 27 is going to be 54 over 3 minus 2 over 3 plus 6 minus 2. So we get that this is equal to 1/4 times 52 over 3 plus 4. And then we have, so 52 is actually divisible by 4. We get 13 over 3 plus 1, which means it is equal to, so 1 is the same thing as 3 over 3, so this is 16 over 3. 3 times 6, well, it's 18, so it doesn't simplify more than this, but this is the correct answer. Okay, so this is the correct answer. Now, this was a lot of work. I just realized before I began, but I decided to continue to do it, that there was an easier substitution that I could have made. So sometimes, and I mentioned this earlier, sometimes you don't want to take the inner function. Had I taken u to be equal to the square root of 2x minus 1 instead of just 2x minus 1, then this would have saved me about 4 or 5, like 4 or 5 steps actually, because I ended up doing way more work than I had to. But again, you still will get the same solution. It's not like you're going to get a different solution. But had I done this substitution instead, I would have saved myself some work. By far, I would have saved myself some work. All right. Let's actually pause it here, and then when we come back, we'll talk about the last thing that I want to talk about for the entire course, and that will be the end of any new material for the class.